Wireless and cellular internet access are quickly becoming some of the most common ways to connect computing devices to networks, and it's probably how you're connected right now. So you might be surprised to hear that traditional cable networks are still the most common option you find in the workplace and definitely in the data center. The protocol most widely used to send data across individual links is known as Ethernet. Ethernet and the data link layer provide a means for software at higher levels of the stack to send and receive data. One of the primary purposes of this layer is to essentially abstract away the need for any other layers to care about the physical layer and what hardware is in use. By dumping this responsibility on the data link layer, the internet, transport, and application layers can all operate the same no matter how the device they're running on is connected. So, for example, your web browser doesn't need to know if it's running on a device connected via a twisted pair or a wireless connection. It just needs the underlying layers to send and receive data for it. By the end of this lesson, you'll be able to explain what MAC addresses are and how they're used to identify computers. You'll also know how to describe the various components that make up an Ethernet frame, and you'll be able to differentiate between unicast, multicast, and broadcast addresses. Lastly, you'll be able to explain how cyclical redundancy checks help ensure the integrity of data sent via Ethernet. Understanding these concepts will help you troubleshoot a variety of problems as an IT support specialist. Warning, a history lesson on old school technology is headed your way. Here goes. Ethernet is a fairly old technology. It first came into being in 1980 and saw its first fully published standardization in 1983. Since then, a few changes have been introduced, primarily in order to support ever-increasing bandwidth needs. For the most part, though, the Ethernet in use today is comparable to the Ethernet standard as first published all those years ago. In 1983, computer networking was totally different than it is today. One of the notable differences in LAN topology was that the switch, or switchable hub, hadn't been invented yet. This meant that frequently, many or all devices on a network shared a single collision domain. You might remember from our discussion about hubs and switches that a collision domain is a network segment where only one device can speak at a time. This is because all data in a collision domain is sent to all the nodes connected to it. If two computers were to send data across the wire at the same time, this would result in literal collisions of the electrical current representing our ones and zeros, leaving the end result unintelligible. Ethernet as a protocol solved this problem by using a technique known as carrier sense multiple access with collision detection. Doesn't exactly roll off the tongue. We generally abbreviate this to CSMA-CD. CSMA-CD is used to determine when the communications channels are clear and when a device is free to transmit data. The way CSMA-CD works is actually pretty simple. If there's no data currently being transmitted on the network segment, a node will feel free to send data. If it turns out that two or more computers end up trying to send data at the same time, the computers detect this collision and stop sending data. Each device involved with the collision then waits a random interval of time before trying to send data again. This random interval helps to prevent all the computers involved in the collision from colliding again the next time they try to transmit anything. When a network segment is a collision domain, it means that all devices on that segment receive all communication across the entire segment. This means we need a way to identify which node the transmission was actually meant for. This is where something known as a media access control address, or MAC address, comes into play. A MAC address is a globally unique identifier attached to an individual network interface. It's a 48-bit number normally represented by 6 groupings of 2 hexadecimal numbers. Just like how binary is a way to represent numbers with only 2 digits, hexadecimal is a way to represent numbers using 16 digits. Since we don't have numerals to represent any individual digit larger than 9, hexadecimal numbers employ the letters A, B, C, D, E, and F to represent the numbers 10, 11, 12, 13, 14, and 15. Another way to reference each group of numbers in a MAC address is an octet. An octet in computer networking is any number that can be represented by 8 bits. In this case, 2 hexadecimal digits can represent the same numbers that 8 bits can. Now, you may have noticed that we mentioned that MAC addresses are globally unique. which might have left you wondering how that could possibly be. The short answer is that a 48-bit number is much larger than you might expect. The total number of possible MAC addresses that could exist is 2 to the power of 48, or 281,474,976,710,656 unique possibilities. That's a whole lot of possibilities. A MAC address is split into 2 sections. The first 3 octets of a MAC address are known as the Organizationally Unique Identifier, or OUI. These are assigned to individual hardware manufacturers by the IEEE, or the Institute of Electrical and Electronics Engineers. This is a useful bit of information to keep in your back pocket because it means that you can always identify the manufacturer of a network interface purely by its MAC address. The last 3 octets of a MAC address can be assigned in any way that the manufacturer would like, with the condition that they only assign each possible address once to keep all MAC addresses globally unique. Ethernet uses MAC addresses to ensure that the data it sends has both an address for the machine that sent the transmission, as well as the one that the transmission was intended for. In this way, even on a network segment acting as a single collision domain, each node on that network knows when traffic is intended for it.